Welcome to Jeremy's IT Lab. This is a free complete course for the CCNA. If you like these videos, please subscribe to follow along with the series. Also, please like and leave a comment, and share the video to help spread this free series of videos. Thanks for your help. In this video, we will wrap up our studies of IPv6. Honestly, there is so much more I want to cover, but this video will be enough to wrap up our IPv6 studies for the CCNA. However, in future videos, I will continue to reference and use IPv6. Some labs will use IPv4, some will use IPv6, some will use both. Same for the examples in my lectures. A lot of people studying for the CCNA don't feel confident about IPv6, and I think it's just because they don't spend a lot of time getting familiar with it. Outside of a few IPv6 specific lessons, everything else is IPv4 in most courses. To review, here are the IPv6 specific topics on the official CCNA exam topics list. The focus of today's video will be topic 3.3, applying the static routing concepts you already know from IPv4 to IPv6. Here's what we'll cover in this video. First up, a correction about my previous IPv6 videos. It's not a big mistake. In fact, it's a mistake that even Cisco makes, but it's something you should know. Then we'll very briefly cover the IPv6 header. We'll also cover Neighbor Discovery Protocol, NDP, which replaced ARP in IPv6. That's right, IPv6 doesn't use ARP. Next, we'll cover something called SLAAC. Finally, the main topic of today's video is IPv6 static routing. Although it's probably the most important section, it's right in the exam topics list, because you already understand IPv4 static routes, it should be simple to learn them in IPv6. As always, make sure to watch until the end of the quiz for a bonus question from Boson ExSim for CCNA, the best practice exams for the CCNA, and the ones I used when studying for my exams. To check out ExSim, follow the link in the video description. So, that correction I wanted to make is about IPv6 address representation, how we write IPv6 addresses. When making these videos, I do a lot of research to make sure my information is as accurate as possible, and I often learn many new things while making them. While preparing these IPv6 videos, I was looking through some RFCs. Let me briefly explain what an RFC is. An RFC, which stands for Request for Comments, is a publication from the ISOC, Internet Society, and associated organizations like the IETF, Internet Engineering Task Force. And these RFCs are the official documents of Internet specifications, protocols, procedures, etc. So if you really want to go in-depth about OSPF, for example, and learn all you can about it, there are tons of RFCs that document OSPF, how it works, etc. RFC 5952 is titled A Recommendation for IPv6 Address Text Representation. Before this RFC, IPv6 address representation was more flexible. For example, you could remove leading zeros from the quartets of the address, or just leave them there. You could replace all zero quartets with a double colon, or choose not to. You could use uppercase hexadecimal, A, B, C, D, E, and F, or lowercase. However, RFC 5952 suggests standardizing IPv6 address representation, so we all write them the same. Here are some of the details from that RFC. Leading zeros must be removed. So this IPv6 address must be represented like this, with all of the leading zeros removed. The double colon must be used to shorten the longest string of all zero quartets. But if there is just a single all zero quartet, don't use the double colon. So this IPv6 address has two choices for the double colon. On the left, there are 3 all zero quartets. On the right, there are only 2. So we must shorten it like this, using the double colon on the left. Then, if there are 2 equal length choices for the double colon, use the double colon to shorten the one on the left. So this address has 2 choices for the double colon. Both are 2 quartets of zeros. So we must shorten the one on the left. Finally, this is the main one I wanted to share. Hexadecimal characters A, B, C, D, E, and F must be written using lowercase, not uppercase. In my videos, I have been using both, sometimes uppercase, sometimes lowercase, but from now on I will use only lowercase. However, I'm not the only one who wasn't following this rule. Here's a screenshot from a Cisco router. Notice the uppercase characters. So this is technically incorrect. However, because even Cisco's devices don't follow this rule, it's not a big deal if you write them in uppercase characters. I guess this RFC isn't very well known, and it's not a hard, fast rule. But let's try to follow the standard from now on. Okay, let's move on to take a brief look at the IPv6 header. Here it is, thanks to Wikipedia for the chart. To compare, here's the IPv4 header we studied earlier in the course. Lots of different fields. Now take another look at the IPv6 header. Much simpler, right? One thing that makes it simpler is this word here, fixed header format. The IPv4 header has a variable header length, from 20 to 60 bytes, but the IPv6 header has a fixed size of 40 bytes. That's why there is a payload length field, indicating the length of the encapsulated layer 4 segment, but no header length field, like there is for IPv4. It's always 40 bytes. The processing of the IPv6 header is much easier for routers, so performance is generally improved. Okay, I won't spend a whole lecture on this header like I did for IPv4, but let me give a brief description of each field. First up, the version field, just like in IPv4. It's 4 bits in length. It indicates the version of IP that is used. Because this is IPv6, this field will always be set to 6, or binary 0110, indicating IP version 6. And that's all there is to say about this field. Next up is the traffic class field. It's 8 bits in length. It's used for QoS, quality of service, to indicate high priority traffic. For example, IP phone traffic, live video calls, etc. will have a traffic class value, which gives them priority over other traffic. QoS is something we'll cover later in the course, so don't worry about it at the moment. Next up is the flow label field. It's 20 bits in length. It's used to identify specific traffic flows, which are communications between a specific source and destination, like the interaction between a server and a client downloading a file. I briefly talked about flows in the TCP/UDP video. Okay, that's all for this field. Next up is the payload length field. It's 16 bits in length. It indicates the length of the payload, the layer 4 segment that is encapsulated in the IPv6 header, in bytes. So a value of 1024 in this field would mean that the encapsulated segment is 1024 bytes in length, for example. The length of the IPv6 header itself isn't included, because it's always 40 bytes. It's fixed. Next is the next header field. It's 8 bits in length. It indicates the type of the next header, the header of the encapsulated segment, for example, TCP or UDP. It has the same function as the protocol field of the IPv4 header. The next field is the hop limit field. Its length is 8 bits. The value in this field is decremented by 1 by each router that forwards it. If the value reaches 0, the packet is discarded. So the function is the same as the IPv4 header's TTL field. Finally, the last two fields are the source address and destination address fields. As you already know, they are 128 bits in length each. 128 bits for the source, 128 bits for the destination. These fields contain the IPv6 addresses of the packet source and the packet's intended destination. Okay, so that was a very brief explanation of the IPv6 header and its fields. I will include flashcards to help you remember the fields. However, I doubt that you will get any direct questions about the IPv6 header on the CCNA exam. But I still think it's good foundational knowledge for network engineers, so I recommend not deleting the cards. Okay, the next topic is something I didn't specifically mention in the beginning of the video. However, it's an important part of Neighbor Discovery Protocol, NDP, which replaces ARP. First, let me just show you how the address is formed. Then when I talk about NDP, you'll see how the address is used. An IPv6 Solicited-Node Multicast address is calculated from a unicast address. Here's how it's calculated. The address begins with a fixed prefix, FF02:1:FF, if you shorten it properly, and then the last 6 hex digits of the unicast address this solicited node address is being generated from. For example, here's a unicast IPv6 address. To generate a solicited node multicast address from it, we take these last 6 digits and then add ff02:1:ff to them. That's it. That's how you generate a solicited node multicast address. Here's another one. Try to write out the solicited node multicast address yourself. Okay, let's check. These are the last 6 digits. Add ff02:1:ff to them, and you get the answer. I showed you this output in the previous video when talking about IPv6 multicast addresses. I pointed out that routers join the ff02:1 and :2 multicast groups by default. But notice this other multicast group that R1 joined, ff02:1:ff36:8500. That's a solicited node multicast address, ff02:1:ff, and then 6 more hex digits. Those last 6 digits are the same as in this global unicast address on the interface. Okay, so now you know how solicited node multicast addresses are calculated. Next, let me briefly introduce NDP and show you how these addresses are used. Neighbor Discovery Protocol, NDP, is a protocol used with IPv6. It's not directly listed on the exam topics list, but just as ARP is an essential part of IPv4 routing, NDP is an essential part of IPv6 routing, so you should have at least a basic understanding of it. It has various functions, and one of those functions is to replace ARP, which is no longer used in IPv6. The ARP-like function of NDP uses ICMPv6 and solicited node multicast addresses to learn the MAC address of other hosts. As you probably remember, ARP in IPv4 uses broadcast messages for the ARP requests. Solicited node multicast messages are much more efficient, being addressed to a specific host, unlike a broadcast which is for all hosts. In the process, 2 message types are used. The first one is the neighbor solicitation message, the NDP equivalent of an ARP request. Note that the NDP neighbor solicitation message is ICMPv6 type 135. I haven't talked much about ICMP in this course. It's a protocol that involves various messages, perhaps the most famous one being ping. After I finish the course, I'll probably make some extra videos about ICMP. Anyway, IPv6 has its own version of ICMP, and the neighbor solicitation message is ICMP type 135. The other message is the neighbor advertisement message, the NDP equivalent of an ARP reply. It's ICMP message type 136. Try to remember those ICMP message types. I'll include them in the flashcards. So here's the basic function of the neighbor solicitation message, the NDP equivalent of an ARP request. Let's say I typed ping 2001 db8:78:9abc on R1 to attempt to ping R2. R1 needs to encapsulate that packet in an Ethernet frame, so it needs to know R2's MAC address. To ask for R2's MAC address, R1 will send a neighbor solicitation message. So R1 is basically just saying, "Hi, what's your MAC address?" Now, to show you how this is different than an ARP request message, let's look at the different addresses in the packet and frame. Below is this message taken from a Wireshark capture, and above I'll explain what each address is. The source IP is R1's IP address. Okay, that's the same as ARP. The destination IP address, however, is R2's solicited node multicast address. How does R1 know R2's solicited node address? Well, it knows the unicast address because I typed in the ping command, and R1 is able to automatically calculate the solicited node multicast address from that. The source MAC is the MAC address of R1's G00 interface. That's the same as in ARP as well. The destination MAC address is a multicast MAC address, based on R2's solicited node multicast address. Notice that in Wireshark, it is displayed as IPv6 MCAST_FF789ABC, but to the right, you can see the real multicast MAC address in brackets. I haven't really taught you about multicast MAC addresses, and you don't need to study them for the CCNA, so don't worry about the details here. Just note that the big difference between an NDP neighbor solicitation message and an ARP request message is that the ARP request is broadcast and the neighbor solicitation is multicast, which is more efficient. Now let's see the neighbor advertisement message, the NDP equivalent of an ARP reply. R2 received a message from R1 asking for its MAC address. Basically, in response, R2 just teaches R1 its MAC address. So let's see the different addresses in the message. R2 will send the neighbor advertisement message using its G00 IP address as the source, and the destination will be R1's G00 IP address. It knows R1's IP address because it was the source address of the solicitation message. The source MAC will be R2's G00 MAC address, and the destination will be R1's MAC address. Again, R2 knows R1's MAC address because R1 used it as the source for the solicitation message. Now, since IPv6 doesn't use ARP, there isn't an ARP table. Instead, the devices will keep an IPv6 neighbor table. Keep in mind, I'm showing this on Cisco routers, but all devices running IPv6 will use NDP, keep a neighbor table, etc. Here's R1's IPv6 neighbor table. You can view it with Show IPv6 Neighbor. Let's look at the output. First, the IPv6 address column. Notice that R1 has an entry for both R2's global unicast address and its link local address. It learned that link local address automatically. I didn't ping it. Next, the age column indicates how long ago R1 received traffic from these addresses in minutes. The link layer address column shows R2's MAC address, and the interface column, of course, shows the interface this entry was learned on. There is also a state column, but for this lesson we won't talk about that. Basically, this reach state means that the neighbor is reachable, so that's good. By the way, this is R2's neighbor table. Feel free to pause the video if you want to check it out. Okay, I will briefly explain one more function of NDP before moving on. This is necessary to understand the next topic. Another function of NDP allows hosts to automatically discover routers on the local network. Again, two messages are used for this process. First one, router solicitation, which is ICMPv6 type 133. Don't mix this up with the neighbor solicitation we just learned. These are sent to multicast address FF02:2, the all routers address. This message asks routers on the local link, the local network, to identify themselves. This message is sent when an interface is enabled, or when the host is connected to the network. The next kind of message is the router advertisement, ICMPv6 type 134. These messages are sent to multicast address FF02:1, the all nodes address. So these messages are received by all hosts on the local link, not just routers. Using this message, the router announces its presence and provides some other information about the link, the local network. These messages are sent in response to RS messages. If a router receives an RS, it will send an RA. However, even if the router doesn't receive an RS, it will send RAs periodically. To give a brief demonstration, I'll use R1 and R2 again. Once again, these functions aren't unique to routers. Although only routers send router advertisements, all IPv6 hosts will send router solicitations when they come online. So let's say we enable R2's G00 interface. It automatically sends an RS message, asking if there are any routers on the link. R1 replies, identifying itself. There are lots of ways this can be used. For example, hosts can automatically learn their default gateway from these RA messages. But let's move on to the next topic, and you'll see another purpose for these RS and RA messages. The next topic is SLAAC. SLAAC stands for Stateless Address Auto Configuration. Yes, another way to configure IPv6 addresses. When using SLAAC, hosts use the RS and RA messages to learn the IPv6 prefix of the local link. For example, 2001 db8:/64. Then they use that prefix to automatically generate an IPv6 address. When using the IPv6 address EUI64 command, you need to manually enter the prefix. We did that in the last lesson. However, the command for SLAAC, IPv6 address autoconfig, doesn't need the prefix. Why is that? It's because NDP is used to learn the prefix used on the local link via the RS and RA messages. Then the device will use EUI64 to generate the interface ID, or it can be randomly generated, depending on the device and maker. Let me show you that on a Cisco router. R1 is connected to R2. R1 is configured with an IPv6 address, but R2 doesn't have one yet. So, I use the command IPv6 address autoconfig on R2's G00 interface. And you can see the global unicast address it generated, and of course the link local address, as always. Once again, keep in mind that although I'm showing you how to do this on a Cisco router, this isn't unique to Cisco. SLAAC is a standard function of IPv6, and end hosts like PCs can do this too, although they don't use Cisco iOS commands, of course. Okay, one final point about NDP before moving on to static routing. This is a simple concept, and you should be aware of it for the exam. Duplicate address detection, DAD, which is another function of NDP, allows hosts to check if other devices on the local link are using the same IPv6 address. Anytime an IPv6 enabled interface initializes, for example via the no shutdown command, or an IPv6 address is configured on an interface, for example a manual IPv6 address or a SLAAC address, the device performs DAD to check if another device is using that same IPv6 address. DAD uses two messages that you already learned earlier, neighbor solicitation and neighbor advertisement. So that's good news. You don't have to learn any new message types. To perform DAD, the host will send an NS to its own IPv6 address, its own Solicited-Node Multicast address. If it doesn't get a reply, it knows the address is unique. However, if it does get a reply, a neighbor advertisement message, it means that another host on the network is already using the address. On a Cisco router, you'll get a message like this if a duplicate address is detected. Exactly what happens next depends on how the IP address was configured, the device maker, etc., but we don't have to go any deeper into DAD for the CCNA. Finally, let's get into IPv6 static routing. As a reminder, here's what you need to know for the CCNA. You should be able to configure and verify the same kinds of static routes that you already learned for IPv4. But now that you're a little more experienced, I'll explain a little more about static routes in general, not just for IPv6. IPv6 routing works the same as IPv4 routing. A packet arrives on one of the router's interfaces, it looks up the destination IP address in its routing table, and then forwards the packet according to the most specific match in the routing table. Although IPv6 routing works the same, the two processes are separate on the router, and the two routing tables are separate as well. You've already seen how the router builds a separate IPv6 routing table. You can view it with Show IPv6 Route. IPv4 routing is enabled on Cisco routers by default. However, IPv6 routing is disabled by default, and must be enabled with the IPv6 unicast routing command. But you already know that. If IPv6 routing is disabled, the router will be able to send and receive IPv6 traffic, but will not route IPv6 traffic, meaning it will not forward traffic between networks. Always make sure to use the IPv6 unicast routing command. If everything about your IPv6 configuration seems correct, but for some reason the network isn't working, there's a big chance that you forgot that command. To demonstrate IPv6 routing, we'll use this network here. But before we actually configure static routes in this network, let's check out R1's routing table as it is now. So here's R1's IPv6 routing table. Just like in IPv4, a connected network route is automatically added for each connected network. A network route is a route to a network, a subnet, as opposed to a route to a single specific host. Also, a local host route is automatically added for each address configured on the router. This is the same as in IPv4. A host route is a route to a single specific host, using a /32 prefix length in IPv4 or a /128 prefix length in IPv6. For example, here you can see the connected and local routes that were automatically configured for R1's G01 interface. a /64 connected network route, and a /128 local host route. Some of you might have noticed this route to FF00:8. That's the IPv6 multicast range. It says via null 0, which is an interface that discards traffic matching that route. So this discards multicast traffic. This route was automatically configured, but it's beyond the scope of the CCNA. If you're curious, try searching on Google for more information. Also, one more thing I'd like to point out. Routes for link local addresses are not added to the routing table. R1's G00 and G01 both have link local addresses on them, but those routes don't appear in the routing table. Now let's actually take a look at static routes. Here's the IPv6 static route command, written in the format Cisco uses in documentation. If you haven't seen a command written like this before, it might be difficult to understand. Although it's not required knowledge for the CCNA, you'll want to understand how to read commands like this for your future studies. This first part is easy enough to understand. The command begins IPv6 route, and then you enter the destination, /, and then the prefix length. Now let me explain this next part in the curly brackets. Curly brackets mean a required choice. So you have to either enter a next hop address or an exit interface with an optional next hop. That's what the square brackets mean. The next hop is optional if you enter an exit interface. Finally, you can see AD in square brackets, meaning this is optional too. What's AD? It's administrative distance, which you'll need to enter to configure a floating static route. Now, there's actually a name for each of these different kinds of static routes, depending on if you specify just the exit interface, just the next hop, or both. This concept isn't unique to IPv6, by the way. It applies to IPv4 static routes too. Let's check out those names. First up, a directly attached static route is a route where only the exit interface is specified. So the command is like this. For example, on R1, you might use this command, IPv6 route 2001 DB803 /64 G00 to reach the network connected to R3. Okay, the next type is a recursive static route, which specifies only the next hop address. So the command is like this. On R1, you might use the command IPv6 route 2001 DB803 /64 using R3's LAN as the destination, and then 2001 DB8012 /2, telling R1 to send the packet to R2. Why is the name recursive? It's because it requires a recursive lookup in the routing table. R1 has to check its routing table multiple times. First, it has to look up the destination. Then it has to look up the next hop to know which interface to send the traffic out of. Let me demonstrate. Here's R1's routing table after configuring that route. If it receives a packet destined for PC2's address, the only match is that route we just configured. It says the next hop is 2001 DB8012 /2. So R1 has to look up that address now. It finds this matching entry, so it knows that it should send the packet out of the G00 interface. That's a recursive lookup. Okay, the next type of static route is the fully specified static route, when both the exit interface and next hop are specified. So the command is like this. For example, to reach that same network from R1, we could enter the command like this. Okay, try to remember these three kinds of static routes. And remember that these are the same for both IPv4 and IPv6. I didn't specifically mention these types in the IPv4 static routing video, but you can have directly attached, recursive, and fully specified IPv4 static routes too. Before moving on, I have to point one thing out about directly attached static routes in IPv6. In IPv6, you can't use directly attached static routes if the interface is an Ethernet interface. So, this command I wrote here actually won't work. G00, which stands for Gigabit Ethernet 00, won't work with this command. Actually, the router will let you enter the command. It will become part of the router's configuration, but the route just won't work. R1 simply won't send the packet. If it was a serial interface, for example, it would work, but not on an Ethernet interface like this. Just be aware of that. Although directly attached static routes work on Ethernet interfaces when using IPv4, they won't work in IPv6. you have to use a recursive or fully specified static route instead. Okay, let's look at an example IPv6 route from each type in the exam topics list. First up, a network route, a route to a specific subnet. I configured this route on R1. IPv6 route 2001 DB803:/64, which is the network connected to R3. Then I specify the next hop, 2001 DB8012:2, which is R2's G00 interface. This tells R1, if you receive a packet with the destination in this network, send the packet to R2. Next up, a host route, a route to a single specific host. For example, let's configure host routes on R2, one to PC1 and one to PC2. Here's the route to PC1, and here's the route to PC2. Since there are probably plenty of other PCs in these networks, we wouldn't normally use host routes in a situation like this. We just configure two network routes on R2. But I just wanted to demonstrate how to configure host routes in IPv6 using a /128 prefix length. Okay, the next type is a default route. Let's configure a default route on R3. Here it is. Notice the :/0, which is like O.O.O.O/0 in IPv4. Okay, so here are 4 IPv6 static routes. Think about the different static route types I showed you in the previous slide: directly attached, recursive, and fully specified. Of those previous types, what type are these 4 routes I just configured? They are all recursive. They all specify only the next hop. Okay, now I left out one type of static route, which is on the exam topics list. That type is floating static. Although this example network here doesn't need floating static routes, how could we configure a floating static route? The answer is here. By raising the AD, we can make static backup routes, called floating static routes. If the main route to the destination was learned via OSPF, for example, you'll need to set the static route's AD to higher than 110, because OSPF's AD is 110. If the main route to the destination was learned via EIGRP, on the other hand, you'd need to set the static route's AD to higher than 90, because EIGRP's AD is 90. Always set the AD to higher than the main route. Finally, I want to bring up a point that I already mentioned in the Day 32 lab video, about using a link local address as the next hop of an IPv6 static route. Here on R1, I tried to configure a route to R3's network using R2's link local address as a next hop. However, I got an error message and the command didn't work. Interface has to be specified for a link local next hop. So if you want to use a link local address as a next hop, you have to specify both the next hop address and the exit interface. So that's what I did. What's this kind of static route called when you specify both the exit interface and the next hop? It's a fully specified static route. Here's that route in the routing table. The reason you need to specify the exit interface is because, with a link local next hop address, the router isn't able to figure out on its own which interface that next hop address is connected to. Okay, let's review before going on to the quiz. First, in this video, I showed you some basic rules about how to properly write IPv6 addresses. Nothing important for the test, but still something you should know. Then I briefly introduced each field of the IPv6 header. It has a fixed size of 40 bytes and is much simpler than the IPv4 header. I doubt there will be any specific questions about the header on the exam, but I still consider it fundamental networking knowledge. Then I introduced Neighbor Discovery Protocol, NDP. NDP is a very important part of IPv6, which serves multiple functions. One of those functions is to replace ARP by using neighbor solicitation and neighbor advertisement messages. Another is for automatic discovery of routers on the network with router solicitation and router advertisement messages. Those router solicitation and router advertisement messages allow hosts on the network to use SLAAC, stateless address auto-configuration, to learn the network prefix and automatically configure an IPv6 address. Finally, we covered IPv6 static routes. Remember those 3 types: directly attached, recursive, and fully specified. Also, network, host, default, and floating routes. All of those types apply to both IPv4 and IPv6, so some of the information here was review, but some of it was new. Remember to watch until the end of the quiz for a bonus question from Boson ExSim, the best practice exams for the CCNA. Okay, let's get started with quiz question 1. R2 sends a message to R1 to tell R1 about the MAC address on R2's G00 interface. What kind of message does R2 send to R1? A. RA, B. NA, C. RS, or D. NS? Pause the video to think about the answer. The answer is B. NA, Neighbor Advertisement. R1 would have sent an NS, Neighbor Solicitation message, to R2 to learn R2's MAC address. In response, R2 sends an NA to R1, telling R1 about the MAC address on its interface. This is like the ARP function of IPv4. RS, Router Solicitation, and RA, Router Advertisement, are also part of NDP, but have a different function. Okay, let's go to question 2. You configure an IPv6 address on R1's G00 interface. What kind of message will it send to perform DAD? A. RA, B. NA, C. RS, or D. NS? Pause the video to think about the answer. The answer is D. NS, Neighbor Solicitation. When an IPv6 address is configured on an interface, the router will send an NS message to the interface's own Solicited-Node Multicast address to perform DAD, Duplicate Address Detection. If no reply comes, it knows that the address is unique. If it receives a reply, it means that another device on the local network is already using that IPv6 address. Okay, let's go to question 3. R1 sends an RA message to devices on the local link to inform them about R1's presence, the prefix of the network, etc. What IPv6 address does R1 send the message to? A. FF01:1, B. FF01:2, C. FF02:1, or D. FF02:2? Pause the video to think about your answer. The answer is C. FF02:1. IPv6 routers send RA, Router Advertisement, messages to inform all devices on the local link about the router's presence, as well as other information about the local network. To do this, the All Nodes Link Local Multicast address FF02:1 is used as the message's destination IP address. Okay, let's go to question 4. You configure the following IPv6 static route. What kind of static route is this? Select 2. So, 2 of the following static route types apply to this route. A. Fully specified. B. Network. C. Host. D. Directly attached. E. Recursive. Or F. Default. Pause the video to think about your answer. Select 2. Okay, the answers are A. Fully specified, and B. Network. It's a fully specified static route because it specifies both an exit interface and a next hop address. It's a network route because its destination is a network, not a specific host like in a host route. Okay, let's go to question 5. Which of the following commands configures a recursive host route? Here are the options. Pause the video to think about your answer. Okay, the answer is C. A recursive static route specifies only a next hop address. A is a directly attached static route, and B is a fully specified static route. C and D are recursive. A host route is a route to a single host, using a /128 prefix length in IPv6, or a /32 prefix length in IPv4. A and D are network routes, and B and C are host routes. So C is the only one that is both a recursive route and a host route. Okay, that's all for the quiz. Now let's take a look at a bonus question from Boson ExSim for CCNA. Okay, here's today's Boson ExSim practice question. You issue the IPv6 route 2001 db8:2 /64 2001 db8:1 :2 command on router A, so that traffic can be routed to router C. When you attempt to ping the Gigabit Ethernet 01 interface of router C, by issuing the ping IPv6 2001 db8:2 :2 command on router A, the ping fails. Which of the following is most likely the problem? Select the best answer. Okay, so here are the 4 options. please pause the video and find the correct answer. Okay, let's check the answer. A, router B does not have a route to the 2001 DB8:1:/64 network. That is probably not the problem. That is a connected network for router B, so it most likely does have a route. Router A does not have a default gateway, so router A does not have a default route. Well, we just configured a route to this network, so there's no need for a default route to be able to reach router C. So B is probably not the answer. Router C does not have a route to the 2001 DB8:1:/64 network. So that could be a problem. For router A to successfully ping router C, router A must be able to reach router C, and router C must be able to reach router A. So router C does need a route to this network. So C might be the correct answer. How about D? Router B does not have a route to the 2001 DB8:2:/64 network. Again, that is a connected network on router B, so D is probably not one of the correct answers, or not the correct answer. So that leaves us with C. I believe C is the correct answer. I'll click on Show Answer down here to check. And that is correct. Okay, here's Boson's explanation. You can pause the video now to check it out. And also notice some references to Cisco documentation. These are really helpful. I highly recommend using the Cisco documentation in your studies to really go in depth on each topic. Okay, so that's Boson ExSim for the CCNA. I highly recommend these practice exams. I use them myself, they're great. And if you want to get a copy, please follow the link in the video description. There are supplementary materials for this video. There is a flashcard deck to use with the software Anki. Note that I have added the tag IPv6 to all flashcards for this video and the previous 2 videos, so you can use Anki to specifically review the IPv6 cards if you feel it is necessary. There was a lot to memorize in these videos, so I think the flashcards will be very helpful. There will also be a packet tracer practice lab, so you can get some hands-on practice. That will be in the next video. Sign up for my mailing list via the link in the description, and I'll send you all of the flashcards and packet tracer lab files for the course. Before finishing today's video, I want to thank my JCNP level channel members. To join, please click the Join button under the video. Thank you to The Gun Guy, L33 America, Brandon, Magrathia, Unjabulo, Sepiso, Justin, Neil, Prakash, Nasir, Erlison, Apogee, Wasim, Marco, Flodo, Daming, Joshua, Gilmar, Samil, Ed, Value, John, Funny Dart, Scott, Hassan, Marek, Velva Jacob, C-Mode, Mark, Yusuf, CD, Boson Software, Charlesetta, Devin, Lito, Jonathan, and Vance. Sorry if I pronounced your name incorrectly, but thank you so much for your support. One of you is still displaying as channel failed to load. If this is you, please let me know and I'll see if YouTube can fix it. This is the list of JCNP level members at the time of recording, by the way. November 1st, 2020. If you signed up recently and your name isn't on here, don't worry. You'll be in future videos. Thank you for watching. Please subscribe to the channel, like the video, leave a comment, and share the video with anyone else studying for the CCNA. If you want to leave a tip, check the links in the description. I'm also a Brave verified publisher and accept BAT or Basic Attention Token tips via the Brave browser. That's all for now.